You've already seen most of the components of object detection. In this video, let's put all the components together to form the YOLO object detection algorithm. First, let's see how you construct your training set. Suppose you're trying to train an algorithm to detect 3 objects, pedestrians, cars, and motorcycles, and you won't need to explicitly have the 4th background class. So just 3 class labels here. If you're using 2 anchor boxes, then the outputs Y will be 3 by 3 because you're using a 3 by 3 grid cell, by 2, this is the number of anchors, by 8 because that's the dimension of this. 8 is actually 5, which is, and then plus the number of classes. So 5 because you have PC and then the bounding boxes, that's 5, and then C1, C2, C3, that dimension is equal to the number of classes. And you can either view this as 3 by 3 by 2 by 8 or 3 by 3 by 16. So to construct the training set, you go through each of these 9 grid cells and form the appropriate target vector Y. So take this first grid cell. There's nothing worth detecting in that grid cell. None of the 3 classes, pedestrian, car, motorcycle, appear in the upper left grid cell. And so the target Y corresponding to that grid cell will be equal to this, where PC for the first anchor box is 0 because there's nothing associated with the first anchor box, and is also 0 for the second anchor box. And so all of these other values are don't cares. Now, most of the grid cells have nothing in them, but for that box over there, you would have this target vector Y. So assuming that your training set has a bounding box like this for the car, it's just a little bit wider than it is tall. And so if your anchor boxes are that this is anchor box 1, this is anchor box 2, then the red box has just slightly higher IOU with anchor box 2, and so the car gets associated with this lower portion of the vector. So notice then that PC associated with anchor box 1 is 0, so you have don't care for all of these components. Then you have this PC is equal to 1. Then you should use these to specify the position of the red bounding box and then specify that the correct object is class 2, right? That it is a car. So you go through this, and for each of your 9 grid positions, for each of your 3 by 3 grid positions, you would come up with a vector like this, come up with a 16-dimensional vector. And so that's why the final output volume is going to be 3 by 3 by 16. Oh, and as usual, for simplicity on this slide, I've used a 3 by 3 grid. In practice, it might be more like a 19 by 19 by 16. Or in fact, if you use more anchor boxes, maybe 19 by 19 by 5 times 8. I guess 5 times 8 is 40, so it'd be 19 by 19 by 40. That's if you use 5 anchor boxes. So that's training, and you train a ConvNet that inputs an image, maybe 100 by 100 by 3, and your ConvNet would then finally output this output volume, in our example, 3 by 3 by 16, or 3 by 3 by 2 by 8. Next, let's look at how your algorithm can make predictions. Given an image, your neural network will output this 3 by 3 by 2 by 8 volume, where for each of the 9 grid cells, you get a vector like that. So for the grid cell here on the upper left, if there's no object there, hopefully your neural network will output 0 here and 0 here, and it'll output some of the values. Your neural network can't output a question mark, it can't output a don't care. So output some numbers for the rest, but these numbers will basically be ignored because the neural network is telling you that there's no object there. So it doesn't really matter whether it outputs as a bounding box or as a class. It'll basically just be some set of numbers, more or less noise. In contrast, for this box over here, hopefully the value of Y to the output for that box at the bottom left, hopefully it'll be something like 0 for bounding box 1, and then just output a bunch of numbers, just noise. Hopefully it'll also output a set of numbers that corresponds to specifying a pretty accurate bounding box for the car. So that's how the neural network will make predictions. Finally, you would run this through non-max suppression. So just to make it interesting, let's look at a new testset image. Here's how you would run non-max suppression. If you're using 2 anchor boxes, then for each of the 9 grid cells, you get 2 predicted bounding boxes. Some of them will have very low probability, very low PC, but you still get 2 predicted bounding boxes for each of the 9 grid cells. So let's say those are the bounding boxes you get. And notice that some of the bounding boxes can go outside the height and width of the grid cell that it came from. Next, you then get rid of the low probability predictions. So get rid of the ones that even the neural network says, gee, this object probably isn't there. So get rid of those. And then finally, if you have 3 classes you're trying to detect, if you're trying to detect pedestrians, cars, and motorcycles, what you do is for each of the 3 classes, independently run non-max suppression for the objects that were predicted to come from that class, but use non-max suppression for predictions of the pedestrian class, run non-max suppression for the car class, and run non-max suppression for the motorcycle class, but run that basically 3 times to generate the final predictions. And so the output of this is hopefully that you will have detected all the cars and all the pedestrians in this image. So that's it for the YOLO object detection algorithm, which is really one of the most effective object detection algorithms that also encompasses many of the best ideas across the entire computer vision literature that relate to object detection. And you get a chance to practice implementing many components of this yourself in this week's program exercise. So I hope you enjoy this week's program exercise. There's also an optional video that follows this one, which you can either watch or not watch as you please. But either way, I also look forward to seeing you next week.